Hello, people, everybody. Oh, jeez. Welcome back. Welcome to English. Um, so today we are in my bed's not made. All right, whatever. And my hair looks like shit. Why did I hit record? All right. Anyway, I'm just gonna do a quick part right now, but we are continuing with the what do you call it? Math Iceberg. So this is gonna be part 2.1, and we're just gonna get it going. All right, let's see. So, and thank you, by the way, for um, all of the love on the first part of this. It's gonna get much more. Uh, it's gonna get much more advanced and much more interesting quickly. So, if that was dry for you, don't worry. It's gonna pick up. All right. Let's start with this iceberg. Elementary algebra. That is just simply you have like 3x plus 2 equals, say, what's a good number? 8. Also, I got a new stylus, by the way, for this. So everybody be excited for the new stylus. I should draw better, hopefully, maybe. I don't know, but we'll see. So 3x plus 2 equals 8, and then 8, if you go minus 2, this is 6, equals 3x. Divide that by 3, divide that by 3, you get x equals 2. Okay, that is elementary algebra. Solving for x, that's how you get x by itself, and yeah, that is how it's done. Um, give myself a 10 out of 10 confidence on that because we're doing a confidence scale. I should put something on the screen for confidence, but anyway. All right, so that's elementary algebra. Next we've got slope. Okay. So take this 3x plus 2 and say y equals 3x plus 2, right? Now, the slope on that, and then the graph would look something like this. It's 2, it starts too high, and it's got a slope of 3, all right? Or, well, yeah, that's what I was getting at, though. The slope on this is 3, because for each one x equals 3 y's, right? You're multiplying by 3. So, or I guess it's 3 x's is 1 y, but that means for every 1 increase in x, there's a 3 increase in y. Does that make sense? So that's the slope. And then slope's going to be important later because if you have something like x squared, right, on a graph that looks like this, then you'll notice that the slope here is, if we draw a tangent line like that, the slope here at this point is different than the slope here at this point. This is a negative slope and this is a positive slope. So, and then also along this curve, right here the slope is low, and up here the slope is higher, right? So that's going to be, but that is slope, that's the slope. What else? Polynomials. Okay. So I'm glad we just spoke on x squared because a polynomial is something like, well, the most general polynomial is can you hear that squeak? What's the word? I was going to say squeeching. That's not the word. Squeaking. Oh my gosh. I worry about myself sometimes, you guys. I really, yeah. Because I can do all this, but I, jeez. Squeeching? Really? All right. Anyway. So this is the most basic polynomial. It's going to look something like that on a graph, right? And, well, actually, that's a terrible example. It's going to look something like that on a graph. And typically what you do with these is solve for the, this the x-axis, this is the y-axis. You solve for the zeros, okay? That's usually what you do with polynomials. That's where the quadratic equation that everybody knows and loves comes into play. Polynomials, folks. That's, yeah. So you have an x squared term, an x term, and then a constant term. And then the constant term is going to shift it up or down. The b, that's the c term. The b term is going to shift it kind of left and right, more or less. And then the a term is slope. That's how, just think about it as like how extreme the slope is comes mostly from the a term. So, yeah. There you go. That's there's your lesson on polynomials. Alrighty. Ooh, see, we get into the deep end quickly here. Okay, matrices, complex numbers, and logarithms. Matrices. Okay, so there's really not. See, because my thing is we don't. Okay, actually, I have an idea. Never mind. I'm a genius. This is why I'm the one making this video, and you're not the one making this video. I'm a fucking genius. Okay, we need to go. We need to talk about complex numbers before we talk about matrices. That's what's happening. Now, what is a complex number? A complex. I'm so proud of myself for. I'm a genius for that. A complex number is something like a plus bi. Okay. Now, this is going to have two. So think about this as that's the way to write the real number line, right? And then this is I times the real number line. Now think about complex numbers as a plus bi, where a is this distance and b is this distance. And so a plus bi would be that point right there. Okay. And let's draw that as an arrow to make it a vector so that we can talk about matrices. 1 second. So this is the complex coordinate plane. Complex, like that. It's a C with this. I'm doing a terrible job. That's usually how it's written, I guess. But it's because it's R. It's I think this is true. I think that's true for my mathematicians out there. But it's a proper subset, or it's a. They are the same. They're equal sets. It has R and IR on it, right? So there's two coordinates in a complex point. Okay. Now we've the A component and the B component, right? Right. So then another thing that's true about these is you can also write a complex point as, because think about this as a 45-degree angle, right? Or pi over 4, right? So this can also be, and then think about this distance as just 1, okay? Um, so this can also be written as cosine theta plus I sine theta, where the sine theta is the distance up it goes, and the cosine theta is the distance this way it goes. And that way, so then you draw it by kind of swinging out from a point. Does that make sense? Like you go along the axis and then you swing out a certain number of radians and you get to your point that way. And so I say this to say that because this is equal, and I'll probably prove this later because it's one of the easier proofs, but this is equal to e to the, because we talked about e, right? E to the x. It grows like that exponentially. I don't know if we talked about e to the x actually. But if we haven't, we will, because e is my favorite number. But complex numbers can be written in this nice form of e to the I theta. And then you just put it's just like a e to the I theta to make it longer. You know what I mean? You just multiply by a number and it makes it longer. So those are complex numbers. Now, matrices. So what do we do? So think about it like this. You could write a number like 1 as 1, or okay, so remember a plus bi. There is the real component and the imaginary component. Now, another way of writing this would be a, b, where a, b is this is a matrix multiplication. So there's 1 and I, right? And then how you multiply, okay, so check this out. This is a matrix, a 2 by 1, 2, no. This is 1 by 2 matrix. 1 row, 2 columns. And this is a 2 by 1 matrix. 2 rows, 1 column, right? In the columns of the first matrix, is just 2, has to equal the rows of the second matrix, which is 2. So for us to do this multiplication, but in this case it works. So you do 1 times a plus b times I, or I times b rather. But you see, you multiply, this is a way of condensing this equation, is just to write it as a, b, because you know you're multiplying it out like that. So this is what is known as a vector, this a, b, or this sideways 1i. That's a vector. Now, if we multiply it the other way, a, b, 1i, we end up with, instead of a single expression, we're going to end up with a matrix here. Okay, so because it's going to be 1 times a, which is a, times b times I, which is bi. Wait. Hold on. Okay, I was tripping for a second here, but okay, so we have to undo this. So this is going to be 1 times a, which is going to equal a, and then a times I, which is going to equal ai, and then this is going to the second column is going to be 1 times b, which is b, and b times I, which is bi. And now we have a system of equations. Now because we have a plus 1I plus 1I. And then, okay, so we don't have a system of equations, sorry, but we have a matrix here. We finally have a matrix. And so what do we do with a matrix? What's, like, okay, so that's how, I'm trying to think, because we didn't have the foundations of having matrices up until this point. But now you can see where a matrix might come from, hopefully, in a roundabout way. If you watch that back very carefully, you'll it's hard. This is difficult for me to explain, but like, so this gets multiplied by this gets multiplied by this gets multiplied by this gets multiplied by this. All 4 separate things. When you have the 2 by, so this is a, let's see, 2 rows, 1 column, that's this one. A 1 by 2 times a 2 by 1, you get 4 entries. A 1 by 2 times a 2 by 1, you get 1 entry, a plus bi. So in this, you multiply this and you multiply this, and then they are added together, which I don't really, that part's hard to explain how exactly, like, the mechanics of that are, I'm going to give myself, because that's a Cartesian product, right? But, yeah. But, or is that the Cartesian product? It's the something product, isn't it? But that's see, now that I'm thinking about it, I don't know why Cartesian products exist in the way they do, which is like, I just know how they work, and like I know the mechanics of them, but I don't exactly know why they did it like that, if that makes sense. Like, it works and it's a good idea, so maybe that's why they did it that way. But like, I'm gonna this is gonna be the first 5 out of 10 I'm gonna give myself on the foundations of matrices. Yeah, that's a tough one. Logarithms. Okay, so most logarithms are, or most logarithms that I use are ln of x. Okay, this was a, here, let's no, we're not done with matrices. Let's give another example. Okay, because really what matrices are for is working out systems of equations. So let's say, okay, we're gonna walk through an example, and I'm not gonna be a bitch about this. Okay, 3x plus 2y equals, let me think. 10. Now, so in this is a rearrangement of the 3x minus 10. Sorry. This is a rearrangement. This can be found from a rearrangement of the, remember the x plus, remember the like, ax plus b equals y form of an equation, right? Like y equals mx plus b. Make that mx plus b equals y. So this is like that over 2. It's the same thing rearranged, okay? Because it's 3.5 x minus 5, or 3 over 2 x minus 5. Yeah. Is y. And then we're rewriting this like this, okay? And then we also have a similar equation of 3x plus 3y. No, wait. Let me think about this. Oh wait, we can go. See, because I have to think about, I have to set this up in a way that. Okay. Okay. So, okay. That took a second to think about. But say we have these equations, right? We have two equations. We have two equations with two unknown variables, okay? That's the situation. This is when, okay, when there is the same number of equations as unknown variables, we can solve for an answer, and we'll get one answer. If we have more variables and equations, we'll get multiple answers. If we have more equations than variables, then some of the variables won't matter. They can't matter. Not everything can matter, I think is how, yeah. You'll get dummy variables that, you could take or leave. So with that, we can now rewrite, remember the matrix thing? We can write this as 3, 3, 2, 4 multiplied by x, y equals 10, 14. Okay. And then, so in this is, this and this are the same thing. They're the exact same expression, just written differently, but it means the exact same thing. So, with that, when we get it in this form, we can set it up in a different way here. We can go 3, 3, 2, 4, 10, 14. And what we can do is called the row reduced echelon form. Now what we're going to do is actually let's just do Gaussian elimination for this. We don't need REF, but okay, so let's take the first row and subtract it from the second row. So that would turn this, and we're allowed to do this with matrices. That would turn this into 3, 2, 0, 2, and then this is 10, and then this is 4. Okay, so now what this tells you is 2y equals 4, right? 2y equals 4 means y equals 2. Okay. And if y equals 2, we know half of the answer already, right? Because we know that it's 3x plus 2y equals 10. And then if y equals 2, then 3x plus 4 equals 10. 3x equals 6. And x equals 2. See how that works? And then likewise, if we try this again with the 3x plus 4y equals 14, we get 8 here equals 14 plus 3x, and then subtract 8 from both sides, we get 3x equals 6 again. and x equals 2. So in this problem is cooked, right? Like I made this problem to have a nice answer of 2 and 2. But literally if you do this with any problem, like any equations, any two equations with two unknown variables, if you put them in a matrix and do this, it will have a solution. Okay. It will. It has to. That's how it works. Unless like there are trivial cases where it doesn't, but it will always have a solution, by and large. So yeah, whew, that is matrices. All right, so we did get through those. Oh, let's see. What is this? Okay. Logarithms. ln of x. That's my favorite logarithm. But most logs are this. Log base 10 of 100 equals 10. Okay. What does this mean? 10. Wait. Is that true? I'm trying to think of how to explain why this is, because you okay, it's log base 10, so 10 down here. Now what do you have to multiply 10 by to get 100? The answer is 10, so that's why this is 10. So this is a roundabout problem where like you say like 10 times a equals x, and then you plug in x and solve for a, right? So in this case, you're when you do log base 10, you're kind of, I'm explaining this like dog shit. What is a logarithm? Maybe I don't know what a logarithm is. Jeez, this video today is brutal, folks. This is a rough video we're going through. If you hold on, if you go here and look, logarithmic integral is my search history, and I don't even know what a logarithm is. It's something to regularize growth rates is essentially what's happening, but that's not really going to do. Oh, is the exponent by which another fixed oh, okay, so log base 10 wow, that makes way more sense. That makes way more sense. Okay. That makes way more sense. No, I know what a log is. It's none of this though. It's literally none of what I just described is true. Whoops, that's a little. That was an error. So let's try this again. What an oversight. Okay, so news for everybody. Log base 10 of 100 equals 2. Not 10. It equals 2.